like outside the ball, generally. Like outside the ball, generally.
Hey everyone. So my name is Shradha and I am researcher with University of Tennessee and a joint scientist with Oak Ridge National Lab. So today I would present my results on deep learning based segmentation of electron microscopy images containing cavities for nuclear reactor application. So this is would be slightly different from what we learned. So in a nuclear reactor, if you have a material and if you have an incident particle, the material gets bombarded with the incident particle, which are energetic. And in a material, you have atom, and then you have the vacancy and interstitial created. And from school science, we know that this is known as Frankel pair production. Now, what happens when this thing happens? Now, when the incident particle collides, as a result, we have vacancy and interstitials. And vacancies can cluster with vacancies to form a vacancy cluster, whereas interstitial can cluster together to form an interstitial cluster. Now, these cluster formation leads to variety of properties that we don't want as a material scientist to be there in the reactor material. And in reactors, we also have helium generation, which comes. Therefore, material evolves like this. So in the beginning, when you start the reactor, when it's just born, you have a perfect material. But after some time, the material starts becoming like a sponge. So you see here, these white ones are the cavities. And these cavities, these are very important for a nuclear scientist to measure them accurately. We need to have exact boundary conditions, exact volume. And if you see here, these objects are occluded. We want to calculate exact area, because even the slight percentage of swelling can give you a very wrong answer in the cavity swelling value. So overall, we will now use computer vision to see how can we evaluate swelling into this material and what can we do to make the process and workflow simpler. So here on screen, you see variety of images. These all are electron microscopy images. And these kind of images, they appear regularly in our domain. And what is the big job is to characterize them, is to know the particle volume and the density and what other information can we take out of it and to assess the material properties out of it. So these different images here, we will study them by computer vision and try to evaluate. So on screen here, you see some dislocations. If there is someone who is from mechanical engineering, he would know what is dislocations. Now here is a cavity that you see, these are the bubbles. And then you have these dislocation networks. So now these are the images that we get, and we will be using computer vision to evaluate different particle densities and volume. So what are we basically trying to do by computer vision? We want to accurately segment them in a way that these objects, their boundaries, are properly separated from their base image, and we can get the volume correctly. Okay, so now coming back to computer vision here, we all know what it is. We know that this is CNN, and I think we learned from the ASIF talk on Sunday about how does CNN works. So if I give a CNN these images of various dogs and cats, we know it will be able to classify it whether it's a dog or a cat. Mm-hmm. We apply the same analogy here, and what happens here, if I give my CNN these images it should be able to tell me this is the cavity 1, cavity 2, and stuff like that. And I should be able to have good results. Now, let us take this talk from basic and let us try to evaluate like what is CNN. So most of you already learned, but some of you who haven't learned from Sunday's talk. So CNN, it's a convolutional neural network. When I give this image, and here I have a bird in the image, and what I want my CNN to train, that it gives me an answer, bird. So a typical CNN, it will consist of input layer, hidden layer, and the output layer. Now we'll just get one by one in the following slides and would learn the concept. Okay. So when we talk about CNN, it generally consists of two parts. First part is a feature extraction part. And in this part, what we will try to do is, we'll try to know if this is, we will try to extract features and would like to classify them, into finally a zebra. But before that, we'll extract features in terms of legs, nose, tail, and everything we can take out of the zebra. And to have this, we have different layers, different processes. So one of the processes we will learn today is pooling. Then we will learn about convolutions and ReLU, that is activation function. And this entire process I will explain in the next slide, and this process is known as feature extraction. And then after the features are extracted, then those image, it is flattened into 1D and then fed into this fully connected layer. And finally, we get the output as, horse, zebra, and dog. Of course, there is a probabilistic algorithm runs here, which takes softmax activation function into an account. Now, before I go to the feature extraction, here's a quick overview, just to simplify this. So instead of the cavities here, to make my explanation simple, I have taken an image, say this is a number 2. Now, this is the image that you give it to your CNN. Now, how does CNN interpret it? Now here, wherever there's a black thing, you see that there is a 0. And wherever there is a white 2, you see them as by number. So this is just a cartoon that I have represented. Now what happens is, this entire image, this is in 2 dimension. We just want to make it into single dimension so that I can fit into my CNN. So this image, I flatten it into 1 dimension. So it is just an image which is read by number is now getting flattened into this matrix. Now what happens? Now we have inside of CNN. So this is your input layer. So all this image, they get into this input layer, right? And this becomes your input. And now inside we have these neurons. Now what happens here? So for example, here you have different, numbers, and these numbers. So this one, this neuron will take the inputs from all these numbers. As you see there, there's a clear connection with all these neurons, and it will add a weight to it and a bias, and that will be your output. So this is the zoom of the neuron inside it. Similarly, depending upon, how many neurons are in the layer and how many inputs, we will have, multiple neurons doing the same thing. And then we have this famous activation function, what it does. So this neuron, which is basically the multiplication of all the inputs by some weight and the bias, it will produce a number y. And this activation function, it will reduce the number from 0 to 1. And finally, we will have this function, which we call it a softmax function, which will reduce and convert these values into probability. And we will have, so for example, here you see the CNN is predicting that, okay, it can be 0, but the probability is 0.29. Okay, it can be 4, but the probability is very low. So highest probability is 2. So this is how a very simple, very easy example that how CNN works. And this is, I went to the last part before coming here, just to tell you that how easy it is if you try to understand it. Now, going to this part, which is a feature extraction. So before flattening it into the numbers, let us see what happens here. So I have taken another number. So just to simplify, and I've not taken an animal here. So in this number, how many features do you see? You see a loop, you see a line, you see a diagonal, and you see here a diagonal and a line and a loop. Yeah, 3 features here. And now we know about a common term that is known as filters. So let us see a cartoon representation of what is a filter. So because it was a talk of 1 hour, so I thought to take it from basic. Now, this is the image here, and this is your 9. So if you see here, this is your 9, which is formed by the digit 1. And rest, everything I've kept in -1 to be simple. Now, what is a filter? Now, in a filter, you can, this is just for a representation, I have given this filter, this is a 9, and we are trying to extract the feature that is your circle. So you see here, 1, 1, 1, 1, 1. This is your circle, and -1 is the background. Now, this is filter, and what happens is when you design your algorithm, you can choose number of filters, which could be 32, 64. Generally, it is 2 raised to the power n. And now you will slide this into this image, and once you start sliding, so what happens is filter, it multiplies with the image and it gives you a number. And you can slide it, this filter will be slided as a step of 1 or 2, and finally it will give you a number wherever it sees a loop. So this thing where we have this, multiplication of filter with the matrix, it's known as convolution, and the term convolution comes from here. Now, see how beautiful this image is. Now, we had this 9, which was on the image. Again, the same thing. 1 represents the 9. And what we are trying to extract is a loopy pattern. So we know that here is the loopy pattern. I started sliding my filter. And so here, wherever, when it multiplies it, we get a number. Now, we also have this one. So here, just an example, because there were 3 features, so there are 3 kind of filters. So another filter is this. And the third filter is this. Just an example to make the representation easy, as I had time. So now what happens? Now, we have a CNN. I input a lot of images into it, and I want to classify them. I want to classify them as 0, 1, 2, 3, 4, 5, 6, and so on. And now I start applying my filter on various images. So this is a loopy filter, which you see as 1, 1 are present around the boundary, -1 is here. Now, when you multiply this filter on this image, wherever there's a loop, you get a number 1. Great. This is for 9. Now, what happens for 6? We have a loop here, and it multiplies here. We have a number 1. Okay, this was a filter. 8, there were 2 loops here. We get a number 1 and 1. And then here, we get a number here and here. I think now I'm able to make my point how these filters are working and extracting the features. So in this way, you can extract features. Here I showed a very simple example. And this is how the feature extracted through filters, which are nothing but a grid of numbers, which get, convolution or multiplied with your image. Now, this is an example, and this image I got from Code Basics, a very famous YouTube channel. So what happens here? This is an animal koala, and we are trying to detect eye. So if I slide my filters over this animal, I find here that image, this is 1 and 1, because there were 2 dots, because this is an eye filter, kind of. And here I have 2, so it is here. And here I have 3, so it is here. And finally, I'm able to detect. So in CNN, you will see, I will show you this algorithm. We apply n number of filters. So ultimately, n number of filters will pass through this image. They will extract a different, feature. And finally, they will all be together, combine to call something known as feature maps. So here, this is the complete feature map, the same example. So everything that is round, eye, nose, ears, then you get it for hands, and here you have the complete feature map. And this feature map is finally, which is flattened into it. And then it will give you, then it's the same CNN it goes under. And so this is here, it is like, so you tell your network that it is a koala, and then from the training and the labels, it tries to, reduce the loss function, and then there's a back propagation that happens. And finally, you have your weights that are adjusted. Now, okay, just another thing. So this is one thing, like I went to what is known as filters. Now we'll quickly cover one thing, that is pooling and activation function. So this was image here. This was a filter. This gave you a number 1. And you see that there are all these extra number that will come out of the multiplication and would be in the network. That is why we use a ReLU. So what ReLU does, it neglects all the numbers between 0 and -1 and keeps all the numbers from 0 to 1. So why are we doing this? Because this kind of step is very important to reduce the computation. These were all extra numbers. And also, we also reduce the linearity when we apply these activation functions. Now, quickly, we also touch the concept of pooling. So when your filter, it multiplies with the image, you have this big grid, your feature is here. I apply activation function. I get rid of all these negative numbers. And finally, I have something like this.
Shradha, can I ask you a question?
Yeah.
If you go back.
Can we do the question after the seminar? Yeah, that will be easy. So here, this is the numbers I have, and then I have the concept of max pooling. So this is a very common concept that we come in CNN. Okay, what is a max pooling? Basically, I'm trying to reduce this big grid of numbers to these small ones here. And what you see is, like, I'm doing pooling, and I have taken all these, I'm trying to have the maximum numbers, and rest, everything is converted into zeros. And this thing where, this is just, I'm taking the maximum out of the matrix and trying to reduce into a matrix which still consists my initial feature. So it's just a mathematical operation. And finally, this was my animal. I was able to do convolution activation function, was able to get these features out. After features, I had a very big, dense array of numbers. I reduce it by a mathematical operation called pooling, taking the max out of that grid. And then I went again into convolution and ReLU. You can add as many layers as you want. And you can add these layers to make your network as big as possible. If you have a very, very, high resolution image, it will become more and more, you will need more and more layers. And finally, you flatten them, and the procedure that I already explained, that it goes under. Now, let's look, and how do I apply this to my images here? So this is again the same thing. So my images are like this. They are not animals. They are very, very bad. And unfortunately, this is the kind of images that we get very commonly in material science, in healthcare, in a lot of manufacturing problems. And what we have to do is, I have to ask my student to please come and, start labeling them. What is the main problem here? We don't know where are the boundaries. Objects are occluded because these are microscopy images, which are basically a projection on this flat, on this flat, how to say, a paper projection of a 3D. So it's a 3D body in the beginning, and the projection is on the flat. So these 3D objects, they look like this. You have to imagine that this is like a football. If I convert this into a 3D volume, this cavity will be like a football. So it's like literally a cavity inside the material, which is formed in nuclear reactors. And now, what I asked is, I have a lot of students working for me, and I asked them to please label them. And this is how student label it. So finally, even student doesn't do a very good job, because this is what we see by eyes. But guess what? Computer vision does a much better job. So now this is just an example that you will have these features, and we have filters which will give you these features out. So anyone who is a beginner in computer vision, it's literally a 2-line code that we know. And literally this model is known as a sequential model. And this is a convolution because we are doing convolution 2D here. This is the number of filters. This is the size of filters. This is the shape of the image and activation function. And here you added the operation max pooling. And this is the entire thing is what I explained to you in so many slides. It's damn simple and easy. It's a 3-line code.
Wow.
And then it just gets flattened, and we can have this entire thing running in 4 lines. And finally, here we are compiling the model, where we are getting into choosing the right optimizer, the metrics, and things like that. Now, see, when it comes to theory, it's very simple, but in the labs, what happens? This is the kind of images that we get, and if I give my students to mark them, this is how they mark. But if anyone closely look at it, these are 4 cavities on top of each other, or it could be your 4 different part of tumor with your skin cells on top of each other. And what you see in the imaging, whether by X-ray or by electron, is these objects overlapping on top of each other. And if you give it to someone, because everyone is not a domain expert, what they will do, they will mark it as a third object like this here. But it is not. It's a complete object. So even humans do errors. Here also, if you see carefully, these are 3 objects, and students mark it like this. So human errors are much more dominant, because these are the labeled image given to me by my students, and even giving them a very high quality tutorial. So very common thing now, what we are trying to do is, one of the problem is we want to accurately segment these objects and to know the object boundaries. That's why we are doing the task called segmentation. Other thing that we can quickly do by computer vision is just by counting them. And for this, we use a famous algorithm called YOLO, and you can count them. But the previous task is much more challenging. Now, we know this thing, it's come from a Stanford lecture here, that this is a classification when you can tell that if it's a cat or a dog or a giraffe. A semantic segmentation is when each pixel in the image has got an identity. So here, these pixel, all of them, they have got the identity grass. This has an identity cat. This is the back trees. So this is semantic segmentation to anyone who is a beginner here. And when you talk about object detection is that you're detecting them, right? Dog, it's a dog, it's a cat. And for a finer my problem, because I have multiple cavities and I want to give them name. Dog, cavity 1, cavity 2. Instant segmentation will be, if there are 2 dogs in the image, I can tell them this is a dog 1, this is a dog 2, and this is a cat. So even among the objects, even among the same objects, I can give them the identity. So this is what we are trying to do here into this project. So now we get into the details, how we did it and what are the challenges. So for the common object detection, we know these models, right? These are the famous model that is in the field. So we have RCNN, fast RCNN, they're from the same family. Every 6 months, they had an improvement over these models. And finally, the latest one that everyone uses is mask RCNN. Then we can use YOLO or SSD for detection. This is just some famous models, if anyone doesn't know about it. And then what we are using here is a UNet model for the segmentation. So in UNet, what happens is we have an input image. Then this input image, as you see, we kind of encode it. How do we encode it? We simply do the same procedures, convolution, max pooling, and a big image we try to reduce into a very small feature here. And then we have something which is known as, here it was encoded, as I showed you in the previous one of the slides, a big image, after Max spooled it became a small. And encoding one, the small image now, it becomes and carries all the feature. This is the kind of model that we are using, and to have the mask. So this is the defect segment model that we are trying to use. It's the same thing. We have an image. It tries to do all these procedure. It reduces the image into small. Why do you need to reduce it small? Because we are extracting the features and we want the features to be there. And then after computation has happened, we have classified them. Then we start to decode them and make them big. Simple procedures we know. When we have a data set, we divide the data set into, what is the data set? We will have 500 images of these cavities and these voids that I will split them into train and validation. And these images, they would be divided into train, validation, and test. And I will have in a folder called labels or the mask here, which I would show you in the next slide, that we will put them. We can use some image augmentation. Image augmentation will be that I have this image and I rotated them, I tilted them, I added some noise. And in this way, I know that my network, when it will be trained, it won't overfit itself. Now here, now we give them into CNN, okay? And then comes the bigger thing, that we are trying to get something on the loss and the accuracy. So here in my study, I'm playing a lot with different kind of loss functions to see which of the loss function does a best job at segmenting my boundaries. And then I'm finally evaluating my model. There's a term called confusion matrix for that. Now, so this was, if you see here, this was the initial image that was there. If this is an overlap, it is written, but the initial image was same. Now, when you talk about ground truth are actually the mask given to me by my students who don't do a very good job, because you see here, these three objects, they made into one. Now, these are the mask. So as I said, when you start these objects here, so you put 500 images of them. Please ignore the term overlap. It's the same. I don't have the right image right now. And then it's the ground truth, which is the mask. And now this is what is predicted by my CNN network. Now, when you see here, this is by my CNN network. And we commonly know that, you have false positive, you have true positive. And what are these false positive and true positive? So positive here is, of course, your white pixel that it is producing. That is why it's a true positive. And if this network somehow produced a false pixel, white pixel, it will be a false positive. So here you see, now this is actually a ground truth. And this is what my image has predicted. It is overlapped by the mask here. And this is white positive here. And this is white positive. And this is actually false, because you see here extra it is predicted. You see here, this is more clear in this image. So this is all is false, false positive. And when you talk about negative is this black pixel here, and this is negative. And then what is false negative? False negative is that actually it was supposed to be white, but it made it black. So this was supposed to be white, but it made it black. So this was the actual thing. So this is the overlapping. So a confusion matrix, basically what happens is, now you have all these parameters: true positive, false positive, true negative, false negative. Now mathematicians, what they have developed, they have called something called accuracy or precision or recall or F1 score. This is nothing, different formulas using the same true positive, false positive, and trying to calculate if what is the accuracy of my model? What is the precision here? What is the recall, or what is the F1 score? Now, let's look here. This is how here different, this is a confusion matrix, and this is the general formula that we use. And these are very famous matrices that we have. One is your Dice coefficient, Jacquard coefficient, and this one. And so what we do is, now comes the main part of the presentation, that we have used different loss functions into my CNN, and I tried to compare different loss functions. Now, for each loss function, if you see here, when I showed this code here, I can choose here different loss function. Here, when I compiled my model, I can use binary cross entropy, I can use Dice, I can choose IOU, I can choose, from the variety of loss functions I proposed, I can choose any, right? And now, what is the main thing that we see here? So these kind of images, they are known as imbalanced data set. Why do we call them imbalanced data set? Because you see the black pixels are much more than the white one. And these kind of images are present, especially in the microscopy area, everywhere. And these kind of images are much more difficult to assess. So you see here, these are all negative pixel and these are positive pixel. So what we see here, this was the original image that we get. These were the predicted mask that we get from this CNN model that I used, UNet. And these are the human labeled ones. And this is the overlap. So some people say, oh, they are okay, you get these values. But if you're doing any precise scientific study or a medical study, no, this is not okay. Because once you overlap them, what do you see? The mask that my CNN has produced, it has got very, very, broad boundaries. So if I'm taking this, if I'm measuring the cavity swelling out of these thing, the values are off by 5%, and 5% is a big number for reactor application. So what we try to do is, now here, this one is, so I will just show you different loss functions we use. So this one is known as intersection over union. It's very famous, very common. So in IOU, what happens is, so when we try to, so this one, IOU is basically, on numerator, you have an overlap. So area of overlap, when it is divided by area of union. Ideally, if the system is very good, we want to make it 1. Right? And this is, we are trying to minimize this loss function. Now, similar to Dice coefficient, there's another Dice loss where we are simply, it is a very similar thing, but they are just using 2 into area of overlapped and total area and try to calculate the value. And then the third one, which people find it a little bit difficult to understand, is binary cross entropy. Basically, it measures the difference between actual and predicted mask. And so here, if this was my predicted mask, this negative pixel and white pixel, their probabilities are compared to their original mask. And from where it tries to learn. And it tries to make the loss 0. Now, if you just remember this formula here, it's something I think Asif also discussed a couple of times here. So this formula, this is a binary cross entropy, and we try to implement this. Now, these are the values quantitatively by applying different loss functions, and you see that values are quite similar to each other. And I will introduce something that we created, a special loss function called distance. And these values, they are here, and you see them, they are quite good quantitatively. The precision are between 0.84 to 0.88, which is okay. Accuracies are also similar, 0.95. But let's do qualitative analysis. So when you do qualitative analysis, if somebody pays very close attention, so if you see here, this is weighted binary cross entropy. So for imbalanced data sets, we use binary cross entropy, but we add a weight to it. This is an artificial coefficient that we add so that we get rid of this imbalanced data set. Now, what happened here is, you see here, so if I quickly change this images, you see here very quickly that WBC here and distance loss function in WBC, for example, you see everywhere it has predicted more whiter area. And if you do, if I analyze them using OpenCV, and if I try to take the values out, WBC has given such a strong error. So everywhere now it will be more clear in this image. WBC, this is an artifact that I'm trying to show just to make my point. The WBC has given more whiter area as compared to distance loss function. So what is happening here? Everywhere wherever I have used WBC, my false positive is so high. Not only that, the boundaries that are around it, they are bad as compared to my distance loss functions. Now, mathematically, what is happening? So this is a very common practice that people use in healthcare, in manufacturing, wherever we have these kind of imbalanced data. So this, if you see here, this is this formula and this formula, they're almost same. We artificially introduce a coefficient here into this formula beta, so that we just say, hey, we have taken care of this imbalanced data set. Now our negative and positive, by including this coefficient, I have made them balanced. So this approach is very common. I have like 10-20 papers who does it, and every time we have qualitatively bad results. So what we did, so the other results that I showed you were from distance loss function. So this is a common loss function that people usually forget, but recently it has become very common in the literature. So this is a loss function where they take into account the information of the boundary in a way that they weigh points closer to the boundary higher. So they weigh the points which are closer to the boundary higher than the points away from the boundary. So they are actually giving more emphasis to the boundary. And you see here, the formula is the same. So they include binary cross entropy, and they introduce a coefficient here. So in science and mathematics, changing the formula. So this was the formula that was created with one of my peers who changed this entire implementation. So generally, this is something if you Google it, you will find it, weighted binary cross entropy. And we changed the formula. This was something created with University of California. And then they introduce a coefficient here where they give more waypoints to the boundary, and we have much better information. As you see, the values are much more better. And for our application, for any medical application, this really matters a lot. For example, this is some of the paper that somebody did in the crack segmentation. So WBC, you see what kind of image segmentation it gives versus what we can get by using another function here. We are using a function, IFW. It was similar function to distance loss function, and you see this improves. So this has a very broader application where we are trying to segment images. So there are more application here. You see that this comes from some medical image where they're literally trying to use the same thing. They have different loss functions, dice, bounding boxes, and they are trying to have a very precise information of the boundary here. And they really want to separate the boundary. And it's a very active field, and we all are trying to work on it. So main summary was that we use the UNet for semantic segmentation of helium bubbles. We say that WBCE, which is the most common loss function used for imbalanced data set, doesn't work for our data sets. And we went for some more special loss functions called distance map loss function. And we compared different other loss function, which gave us quantitatively same results, but qualitatively results were really bad. And this thing can be directly implemented to other fields called medical or in additive manufacturing, etc. I can take the question, but very quickly, I will also pass through this thing. Like apart from that, our lab also did, all kind of analysis using YOLO and Maskar CNN. So in Maskar CNN, what you get is you get instant segmentation, because we were very much looking forward to the fact that we wanted each cavity or everything to evolve with time, because here this was somewhere, in the, if you see here very carefully, this is some paper that I'm recently publishing. So okay, this is not embedded, but this was the image where cavities, they try to merge into each other. Sorry, this video did not work. Somehow it was the link that I put. So if you see here, this is the video where these cavities, you see that they keep on vanishing and evolving. And we are trying to do and try to analyze them to see where these cavities they go. Do these in situ life studies. Therefore, to have the identity of each matrix was very important. Yes, thank you.
For questions?
Yes, I finished on time.
Yes, you did. You
Okay.
have time. There's no time limit.
Okay.
So maybe you would like to take questions.
Yeah, I'm open for some questions.
This kind of project, like how long does it take to implement something like this?
Would you mind, great presentation, by the way, would you mind going back to the quantitative measures that you had, and can you talk a little bit about that, how those,
This one?
Yeah.
Yeah. So it really depends on this kind of problem, right? So for some problems, for us, the main thing that we were doing was that we wanted really a very precise volume of the cavities, and we wanted boundaries to be perfect as possible. We wanted a precision of, really 0.5% or something. But if you talk about the precision, recall, accuracy, F1, these are different metrics that you get out of, these formulas that I have shown. So you plug in the loss function and you get these values. Then, you can get ground truth. Sorry, you can get false positive, true positive, and these values out, and you can calculate them. And you can calculate different values, precision, recall, or accuracy, and stuff like that.
got
Yes.
it. Thank you.
Yes. No question.
No, so like you, and similar type of problem, right? If I have to analyze this material year after year after year, I take a snapshot. So in my use case, right, we build telecom towers,
Okay.
right? And every year we have to give insurance company health of the tower, right? Especially after hurricanes.
Yeah.
In Florida area.
Yeah.
Right now, I don't think there's a good way out there. So the idea is, right, you send a drone, you take a picture of 100 towers in Florida.
Yeah.
And you take picture next year, take
Yeah,
another picture
yeah.
to see how much tower has deteriorated, right? So that will decide the insurance cost.
Yeah.
That's why I was asking, how long does it take for to develop something like this?
So I think for you don't really care precisely about the boundaries, because it's not a microscope. It's a rather a macroscopic problem where, I can measure distances in centimeters and millimeters.
Right.
What I showed you was we were measuring in nanometers.
You are, yeah.
Yeah. So if you have millimeters or centimeters, then any algorithm can do it. You would need at least just 10 images, and you need to label those 10 images, and process can be done in a day. If configuring the entire CNN, labeling the images, and running the model, and most of the segmentation model will do your kind of job very easily. It just comes the problem when you have these blurry images and bad images. to take information out of them, it's a kind of a big deal.
That's where the challenge is.
That's
there,
a
because
big
nanometer
challenge.
level,
Big challenge.
cavity level.
Yeah, when you're really at atomic level, then becomes a challenge. But for anything that is macroscopic, something that I can see by my eyes, it's not a challenge. It's even a day projects, and if you go at YOLO or you go at UNet website and code, there are hundreds of data sets.
I think you had a question.
I had a question.
Yeah.
If you can go back to that, the loop that you were creating around the 9 and the filter that you were running.
Yeah.
I was just trying to understand how there was only one.
This is just a way to explain. This is just. I really like this explanation from Code Basics. That's just a good way to understand. So basically, in the beginning, your filters that you do, they are random. They just don't have these weights. It is just a way to say, like, finally, your filters, they will have the weights like this, which will have information from this area, which will have a similar kind of, numbers or weights. It should be able to take that information out. Just a representation.
Just curious, this is also part of the deep learning as well, right?
Yeah, CNN is all deep learning. Wherever you can add neurons to it, it becomes deep learning.
Mm.
And a lot of this is also based on the model selection, right?
Yeah.
You said you use the unit model, but from what gives you?
CNN, it's
How would you even go pick a model, right?
Yeah.
Because you might end up picking a wrong model, and this could be like you're either spending more time, energy, and the infrastructure.
Yeah.
Is that an art more than a science?
Well, it's normally all the advanced models that they come, they can easily do the tasks that previous models have done, generally. But then there are use cases. For particular use case, that model works best. For me, I choose UNet because I was only looking at masks. And there were masks in the UNet. I don't really care. So UNet is done for semantic segmentation, where I really don't care, that this is cavity 1 or cavity 2, cavity 3. All are same. It will just give me a black and white mask. And then it is me. I have to use another algorithm. I used OpenCV to have the values of cavities and everything from the mask. Now, other algorithm was mask or CNN that I used. And mask or CNN, I wanted here, as you see, that one of the videos I showed you where cavities were evolving. So I just wanted to really go deep and wanted to see where that particular cavity is going or where that particular cavity is merging so that I can say that this is cavity A or cavity B or cavity C or cavity D. And for that case, I need something called instance segmentation. And Maskar CNN has been quite a hero known in this field. But then again, when you apply this, then you have to customize it. Like I customized it with using a different loss function. Somebody with University of California helped me to develop it, understand it. And it looks a very easy presentation, but when you start doing it, you don't understand anything, mathematically.
I can vouch for it.
Yeah, you have variety of distance functions. Yeah.
But again, like so your loss functions, right? Let's take that as an example. You showed 5 or 6 different loss functions, and you also mentioned that somebody helped you develop a brand new loss function.
Yeah.
You don't know anything. She said it. You don't know anything.
So, but the model selection as well as loss function selection.
Yeah.
It's more trial and error, like loss function. Let's say model. You said okay, every model performs better than the previous model. Therefore, you won't miss much if you pick any model.
If you pick advanced model, you should not miss much in general.
Okay. But loss function selection, is there something?
It's a big debate. It's a big debate. That's why you have a library of loss functions available for different problems.
So okay.
The most common people used in image analysis is like I started with intersection over union with dice loss. This is like something that anyone, even somebody would say that use it. And then you see, hey, my results are not good. What should I do? And
So then you start experimenting with your loss functions?
then I start experimenting with my loss function.
Got it, okay. Because that IOU was more confusing because that showed up as a loss function that also showed up as a measure.
Yes, yes.
So-
So that is also a performance matrix, and the performance matrix like can be converted into a loss function. So basically it was 1 minus that IOU,
Okay.
right? So you want, so I can add here. So you want intersection over union to be 1, right? Then you are perfect. And you want your loss to be 0, right? So 1 minus 1 would be 0. So that is how these loss functions are created. So they just have a performance matrix, and and here in the dice as well, it's the same philosophy.
1 minus that.
Yeah, but you see, in any of the loss functions that I showed you, for example, this is WBCE. This is a mask given to me by the use of WBCE. And I can simply calculate my intersection over union from this as well, right? Who stops me? I can calculate and I can give the value. So this will be a comparative performance matrix, right? So for all the loss functions, you can calculate whatever you want. And there are only some where your loss value is between 0 and 1 that you can able to convert it into, loss functions.
When it comes to accuracy, I saw the accuracy ratio was 0.81-ish.
Yeah.
So, actually, never mind. So, what if, what would be like the standard, not standard, but then like the line that can be marked
So,
as,
yeah.
or we can use this as an enterprise level?
Yeah, so it's a use case. For us, I think 0.95 was quite good. It's 95%. We, like, people in my group were happy. They were more concerned about, the boundaries. But if I have a use case, if you are just counting cars in the parking garage, 5 cars are missing out of 100, you won't be happy, right? So it literally depends on the use case. Like if I give you there, you want 100%, I want 100 out of 100 cars.
So every use case.
Yeah.
But CN, like this cavity, right? I mean, if you make a circle around it, right? But CNN can tell you how big is this area.
Yeah.
That's something you have to write some more.
Yeah. So
Code.
this is just an object counting problem. So once you have these masks, right, then also there is a lot of algorithm that you have to do. So you have to try to fit them into circles or some kind of a dimension or a box, and then you get the values out.
Okay.
And in mask CNN, that problem is totally resolved because in a way it directly gives you these values, right? And then also here as well, you have to use an additional algorithm. We use OpenCV, so yeah.
Yeah.
Thank you. It was helpful.
Any other questions?
Thank you. This was a great talk.
Thank you.
Thank you so much.
Thanks.
Thank you.
All right, folks, thank you for being part of our support vectors meetup. If there are no more questions, then I would like to close the session. And Shradha, well, once again, thank you for your great presentation here.
Thank you for coming. I really appreciate to have the effort coming, especially in the evening.
I know
that's
that's good.
good.
Biryani.